The last kinematics quantity that we have yet to learn about with its angular equivalent is momentum. Let's first start out by asking, when does an object have momentum? Well, we know an object has momentum when it's moving. That means that an object would have angular momentum when rotating. The equation for linear momentum we learned is momentum is mass times velocity. The equation for angular momentum is similar. The symbol for angular momentum is a capital letter L. It is also a vector, just like linear momentum. Instead of mass, we use its rotational equivalent, or moment of inertia. And instead of linear velocity, we use angular velocity. Typically, we write this equation without the vector symbols, but it's good to remember that angular momentum, like angular velocity, have a direction, and for our purposes, we'll use clockwise or counterclockwise. Looking at the equation will help us figure out the units. We know moment of inertia is measured in kilogram meters squared, and angular velocity is in radians per second. But remember, when we multiply anything times radians, the radians disappear. That means we're left with the per second part. So the units for angular momentum are kilogram meters squared per second. I wish we had another name for that, but unfortunately, we'll just stick with the kilogram meters squared per second. What else do we know about momentum? When we learned about momentum, we learned a couple of other rules. Mainly, we learned that the change in linear momentum was equal to the force times time. We called this the impulse momentum theory. We also learned that linear momentum was conserved. Guess what? We can use these two rules in a rotational form as well. So if this is the linear version, then the angular version would be that the change in angular momentum is equal to the rotational form of force, which is torque, times the change in time. And also, linear momentum is conserved. While we don't use the angular momentum impulse theorem a whole lot, we do use this conservation of momentum theorem quite a bit. We'll focus on calculating angular momentum and using this conservation of angular momentum theorem in some example problems. Let's look at one of those example problems now. In this example problem, there are two children, Kevin and Ellen, who are standing on a playground merry-go-round. Merry-go-round, we're told its mass and its radius, and that it's shaped like a solid disk. We're also given Kevin and Ellen's mass, and the fact that both of them are standing on the edge of the merry-go-round. In other words, their distance from the axis of rotation is the same as the radius of our disk. We're asked to calculate the magnitude of that angular momentum of the system, given that Kevin has a tangential speed of 2.1 meters per second. To solve this problem, we'll need to start by calculating the angular momentum of my system, or the total angular momentum. We can do that by adding together three different values of angular momentum. The angular momentum of the merry-go-round, plus the angular momentum of Kevin, plus the angular momentum of Ellen. The merry-go-round, it says, is a solid disk. And if I look on my equation sheet, I find that the equation for the moment of inertia of a solid disk is 1/2 mr squared. Kevin and Ellen are not rotating about an axis that is on them, but rather the axis is far away from them. Therefore, we'll use mr squared for both of them. When I plug numbers into this equation, the mass of the merry-go-round, it says, is 153 kilograms, and it has a radius of 2.4 meters. That's that same R value that I'm going to plug in for all of these quantities. So really I could simplify this to saying 1/2 times the mass of the merry-go-round plus the mass of Kevin plus the mass of Ellen times the radius squared. Just makes it a few less numbers that I need to plug into my calculator. Go ahead and pause the video, plug those numbers in, and unpause once you have an answer. Hopefully you calculated the moment of inertia to be 814 kilogram meters squared. Now that I have that moment of inertia, I know that I can use that, plugging that into my angular momentum equation. And really, I'm just going to focus on the magnitude of the angular momentum in this case, because I'm not told what direction it's rotating. But I can find the magnitude of that angular momentum knowing this moment of inertia. 814 kilogram meters squared. But unfortunately, I don't yet know the angular velocity of my merry-go-round. But there is another piece of information I'm given. I'm told that Kevin, who's standing on the edge of the merry-go-round, has a tangential speed of 2.1 meters per second. And I know that there's a relationship between that tangential speed, and the angular speed. The fact that the tangential speed is equal to the angular speed times the radius. So the angular speed would be the tangential speed divided by the radius. I could plug that into my equation up here so that the moment of inertia is I times the tangential speed divided by the radius. So I'm told that it's 2.10 meters per second. And I divide that by the radius of the merry-go-round, which I'm told is 2.4 meters. When I plug all those numbers in my calculator, I find that the magnitude of the angular momentum of this merry-go-round is 713 kilogram meters squared per second. In class, we'll work on some example problems where we'll not only calculate the angular momentum, but look at how the angular momentum is conserved.